Okay, so let's finish this waves thing. Okay, so we're going to look at the dual nature of electromagnetic radiation. Now remember, all of these are part of the spectrum of electromagnetic radiation. So radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma rays are all form part of the electromagnetic radiation. Okay, and we do refer to it as an IMR instead of writing it over and over and over. Okay, so what happens now is that from the video that you saw, you should have seen that scientists have seen that light behaves like a wave, so it has wave-like properties, and it behaves like a particle, and so we say it has a particle-like nature. So that's where the dual nature comes from, because dual means two. Okay, so it's like a wave because it can diffract. Okay, in other words, it can spread out when it travels through a small gap. I think that was shown on the video as well. But because remember, if you think about, I think I've spoken to you about this before, that if you have rocks and you have water, if you just put water waves coming towards the rocks, okay, and when it goes through the gap, you can see how that gap spreads it out. So these are my rocks, and you've got water, straight waves of water, and you see how they curve out once it goes through there. So that's what it means by diffract. Okay, and if water waves do that and light waves do it, then they must have wave properties. It's like a particle because it can make electrons leave a metal, and that's the photoelectric effect. Now, I'm not going to talk too much about this. This we're going to do in matric. I've just finished it off with the matrics now, actually. Okay, so the thing you need to remember is that the speed of electromagnetic waves is all the same, and it actually has a constant, which is a c, and it's 3 times 10 to the 8 meters per second. That is very, very fast. Okay, so this is the speed of radio waves, microwaves, infrared, all our visible light. So green travels at that speed, UV travels at that speed, X-rays travel at that speed, gamma rays travel at that speed. Okay, they all travel at the same speed, and we refer to it as a c. It is a constant, and it will be on your data sheet. Okay, but you need to remember that I'm not going to tell you about the velocity of electromagnetic waves. You need to know, or radiation, you need to know that this is the velocity always. Okay, so it's from the wave equation. We know that the wave equation was v is equal to f lambda. Okay, where that was the velocity of the wave and this was the frequency and the wavelength. But now, because all the electromagnetic radiation waves or spectrum all travel at the same velocity, we can replace that v with a c, and we know that it's always 3 times 10 to the 8 no matter what. And then all we have to do, if we've got a frequency, we can then work out wavelength. If we've got wavelength, we can work out frequency. Okay, so frequency is inversely proportional to wavelength. Inversely proportional to wavelength. That means, and we saw it over here, the bigger the frequency, the smaller the wavelength. So here we have small wavelength, we have big frequency. Large wavelength, small frequency. Okay. The higher the frequency, the smaller the wavelength. Okay, so I should have just put this on a new page, I suppose, but anyway. Okay, so the electromagnetic radiation as a particle. So we're just going to look at this part now. We're not going to look at diffraction at all. So this was quite a nice little drawing that I found, and it shows a light bulb with sometimes behaves like a wave and sometimes behaves like particles. Now, if we think of them as particles, we call them photons. Photons are basically a particle of light. Okay, so electromagnetic radiation has wave nature and a particle nature. So Planck, this is Mr. Planck, Max Planck. Okay, he actually worked with Einstein a bit. So Max Planck made the following assumption. So he said that energy is radiated or given off or absorbed in fixed amounts. So it's like if you were to go up steps, okay, and to go up a step, you need a certain amount of energy to get to that step. If you don't have that amount of energy to get to that step, you're not going to make it up that step. And you're not going to absorb any of the energy or give off any of the energy. You have to make it exactly the amount of energy to get to that step, or to that step, or to that step. So we say it's packets or quanta of energy. Okay. Each quantum of energy consists of a fixed amount of energy for a specific frequency. So basically what we're saying is that here, for each one of these frequencies of radiation, we've got they give off different amounts of energies. Okay. Excuse me. So the higher the frequency, the higher the energy of the photon. Okay, this has a photon. Okay, and it has quite a low energy, so it's pretty safe. And as it goes up here to gamma radiation, the photons are higher frequency and they have more energy. The photons themselves contain more energy. Okay, and only whole numbers of quanta can be radiated, because you don't really need to know any of this theory over here. But what I do need you to know is understand that there's a dual nature and that you can work it out. So we have an equation, and this is E for energy. Okay, energy, and it is measured in joules. Okay, and there is H, which is Planck's constant. Okay, let's just look up Planck's constant quickly because I don't remember it. Okay, so Planck's constant is 6,63 or 66, depending on what's on your data sheet, times 10 to the minus 34. Don't worry about the units for now. Okay, and we times by the frequency of light. So if you have blue, you have a certain frequency, you times it by Planck's constant, and you can then work out how much energy blue light has. Okay, we've looked at the wave equation, so you can see that is C, which is velocity of any of our radiation, and that would then be the frequency times the wavelength of light. Now obviously you can see I have frequency here and I have frequency here. If I manipulate this formula so that frequency is the subject of the formula, that means I'm going to divide by wavelength to get frequency. I can then replace that frequency with this equation. So we can, if we are given a wavelength, we can then work it out like this, where we have Planck's constant times C divided by the wavelength. Okay, girls, you don't have to use that one. If you are given a wavelength and you need the energy, you can get it from here first and then substitute it in here. But it's quite easy and quick to do that. Okay, so we use Planck's equation to find out how much energy do each of these photons have, and that is dependent on the frequency of light. Okay, so I want you to do Think Tank 3. It's just a table that I want you to calculate. There is, oh, I've got a pen mark on my hand. There is a revision exercise as well. If you're finished with this and if you're happy with everything, we will be done with waves. Okay, and I'm going to move on to chemistry. Okay, so I'm going to just quickly do an example from Think Tank 3, number 1. And I'm going to then just work out frequency. Oh, sorry, we were given frequency, we need to work out wavelength. So the way you're going to do that is you're going to use this. Okay, we always know that C is a constant, 3 times 10 to the 8. Frequency is 5,1 times 10 to the 15 and times wavelength. So you take that down. So 3 times 10 to the 8 divided by 5.1 times 10 to the 15 is equal to wavelength. Okay, and you can work that out. I'm just showing you how to do it. Okay, so that'll give you wavelength. Energy of photon, you can then take the frequency and you can use, let me just do it over here. E is equal to Planck's constant times frequency. You're working out energy, so it's Planck's constant times the frequency, which is over there, and you can get the E. To get the type, all you need to do is look at the frequency or the wavelength, take it back to something that's like this. I think there's one in your textbook, and you can then have a look and see where does it fit. Does the wavelength fit somewhere in these categories, or does the frequency fit here? And you can then say, oh, it's X-rays, or oh, it's infrared. Okay, so that's just a very quick and brief explanation on that. Please let me know if you need any more help, and yeah, we'll be done with waves soon.